Hello class. Today we're going to start chapter 19. I don't know. I find a lot of students struggle with this chapter. I don't know what it is. If it's students don't think it's important. If you don't think this chapter is important, maybe because you're like pre-med and you're like, why would I need to know electrochemistry? Well, just think about the electrical conduction of nerves. There's a lot of electrochemistry in the body, oxidation and reduction. You may want to read the last part of this chapter to see why you need to understand electrochemistry. My other thoughts on why people don't do well on this section are you've forgotten the oxidation rules. There are specific rules. They are hierarchical. And they have to be memorized, and maybe you've forgotten them. So what I would encourage you to do is in this TRO book, go back to page 349 and 350 and look at the rules on page 349, memorize those, put them on a flashcard, whatever you need to do. And then on 350, try some of those problems out and see if you can do them. The other key component you need in order to do this chapter is Gibbs free energy. You have to understand it. You have to know that we're talking about a reversible process where the electrons can flow. And again, what is energy? The ability to do work. So in this chapter, we're going to talk about one substance releasing electrons. We get some work out of those electrons, and then they go back into another substance and they reduce that substance. So that's really the overall process here. And my other thought is why students don't do well on this chapter is it's generally towards the end of the semester and there is some fatigue, and maybe you've got a lot of other stuff going on, but just dedicate some time to this. It's really not that hard of a chapter. In fact, to me, this is easier than kinetics for sure, and it's easier. It's not as drawn out as some of the equilibrium problems. So you just got to kind of work through it, and if you do that, you'll do much better. All right, so let's go back and talk about what oxidation and reduction are. You can't have one without the other. And so when a substance loses electrons, we say that it's being oxidized. And when a substance gains electrons, we're saying it's being reduced. So when you look at the chemical equation, sodium reacts with chlorine gas to form 2 moles of sodium chloride solid. What the first rule you should remember is that the oxidation number for sodium, pure element in its standard state, is 0, and the oxidation number for chlorine, which is normally diatomic, in its standard state, which is a gas at 25 degrees Celsius, also has an oxidation number of 0. Now, what oxidation is, it's a way for us to, again, to keep track of what's going on with the electrons. So what's accepting an electron and what's losing an electron. So yeah, if you just have a pure element, the electrons are distributed evenly around the nuclei of the element. And so that's why its oxidation number is 0. Same thing with chlorine, even though there's 2 nuclei there, the electrons are evenly distributed between the 2 atoms of chlorine, so its oxidation number is 0 as well. So the next thing is it's really important that you understand the equations. And so the oxidation equation in purple, you see sodium, we have the yield sign, and then we have a sodium positive ion. So the sodium has actually lost an electron. And we show that loss by saying plus 1 electron. So if you see electrons on the product side of the reaction, that tells you it's an oxidation reaction, that substance is losing electrons. So that's important. And when we look at the next reaction, chlorine in red gains 2 electrons, and we form 2 chloride ions. And so any reduction process, the electrons will be on the reactant side. All right, so these reactions, the oxidation reaction and the reduction half reaction, let's just these reactions, the oxidation reaction and the reduction half reaction, the reduction reaction, are called half reactions. All right, so I'm trying to get that out. That the oxidation reaction is called a half reaction. The reduction reaction is called a half reaction, and you have to have both in order to have oxidation and reduction. So for us, what we're going to generally look at is in oxidation. Again, we generally think of the element losing electrons, but it could also be a compound gains or adds oxygen, and so that's why we call it oxidation. It's gained oxygen, oxidation. If a compound loses hydrogen, that's also called oxidation. Or if the electrons are on the product side, that's also called oxidation. So these are different ways to identify oxidation. For us, we're going to focus mainly on an element loses electrons, and we're going to look at a half reaction that has electrons on the product side. The oxygen and the hydrogen, you should know these. You're going to need to memorize these, even though these are not as important maybe in this chapter. And that's because when you get into organic chemistry, that's how you're going to determine oxidation and reduction a lot of times. The addition of oxygen or the loss of hydrogen indicates oxidation. So reduction must be the opposite. Well, it is. It's an element gains electrons, it loses oxygen, it gains hydrogen, and the electrons are on the reactant side of the half reaction. So here we have a reaction, and it's chlorine reacts with iodine. The iodide ion in water, we form 6 moles of chloride ion, and the iodate ion and 6 moles of the hydrogen ion. So that's the entire reaction. So all oxidation reduction reactions can be broken down into oxidation half reaction, reduction half reaction. So let's look at it. So the first thing, and this is why you need to go back and look at the rules on page 349. You need to be able to look at every element in this reaction and be able to assign oxidation numbers, or oxidation states, also called that. So chlorine has an it's an element. And so, because it's an element, its oxidation state is 0. Oops, let me get out the pen here. All right, so you're up here, and you see that this is a pure element. Its oxidation number is 0. Whatever the charge is on an ion, that's also its oxidation state. So the iodide ion has a -1 charge, so it's got an oxidation state of -1. So then we look at water. Now remember, these aren't true charges. We know water's a polar covalent substance. We know that oxygen is more electronegative than hydrogen. The electrons are going to be spending more time around the oxygen than the hydrogens. So the hydrogen's electrons are spending more time around the oxygen. It's given an oxidation number of +1. Again, there's a rule for that. There's a rule back on page 349 for that. And so that means oxygen is going to have an oxidation number of -2. What I want you to remember here is these are not true charges. Yeah, we said that oxygen is partially negative and the hydrogens are partially positive, and you can think of it that way, but these numbers are assigned as kind of a bookkeeping method of where the electrons are assigned. And so because oxygen being more electronegative, it's going to gain an electron from each hydrogen. So each hydrogen is going to be a +1, and the oxygen is going to be a -2. It's like it's got 2 more electrons than normal. Again, not totally transferred over, but it feels like it has 2 more electrons. It's got a full outer shell of 8 if you want to think of it that way, but it is sharing because it's covalent. All right, on the product side, we've got chloride. It's a -1 charge because it's a -1 ion, -1 oxidation state. Here's something just to keep in mind. This is kind of old school, but if the charge is out in front and then the number, that's an oxidation state. If it's the number and then the charge, we generally think of that as a true ionic charge. I don't know if that rule still holds as much today, but that's something you learn later, or that's the way I was taught, and it's something I still think about today. All right, this is the one that gives students the most problems, this one right here, iodate. How am I supposed to know what the oxidation number of iodine is? Well, first of all, you know it can't be more than positive 7 because there's only 7 electrons in the outer shell of iodine, so all 7 can't be shared. But what you're going to have to do here is, this is why you got to know the oxidation rules on page 349. You'll say X here for the iodine plus 3 times the oxidation rules say that oxygen is always -2 unless it's a peroxide or a superoxide. So we got X plus 3 times a -2, and that's got to equal the charge on the ion. If it was a neutral substance, you would set that equal to 0. Again, page 349 and then page 350 to see how you would do that. And so based on that, we got X minus 6 equals -1. We move the -6 over to the right-hand side, and that makes a positive 5. So that's how you're going to determine the oxidation number of the iodine. This is defined by the rules on page 349 that oxygen is a -2, and then from that you work out this simple problem, algebra problem, solve for X. All right, and then hydrogen's a positive ion, so its oxidation number is +1. You go, well, why do I need to do this? If you will do this, what you can see very easily that the chlorine is being reduced to chloride. It's going from a 0 oxidation state to a -1 oxidation state. So it's gained electrons, and so we would say that's reduction. Now, you look at the iodine, and the iodine has gone from a -1 ion here to a +5 oxidation state. So it's gone from a -1 oxidation state to a +5 oxidation state. And so therefore it's being oxidized. So what I do is I pull that out. I put the iodine here, I put the product here, and then I've got to figure out how many electrons was gained, and you can see from -1 to a +5, we know it's 6 electrons gained, or lost. Yeah, lost. What am I saying, gained? So lost, all right? So 6 electrons are lost. So the reduction is easier because you can see we saw it goes from 0 to -1, and there's 2 for every diatomic chlorine. We form 2 chlorides, so there's a gain of 2 electrons on this reduction. All right? So oxidation, based on those oxidation numbers that you've calculated here, based on the rules on page 349, and maybe some practice on 350, you can do this. All right, so make sure you do that. Refresh your memory, because I find students don't do this, they just don't do well. All right, so then once you can determine what's being oxidized and what's being reduced, the chlorine, break those down into 2 half reactions. Now, it's not balanced. That's okay. What you're going to find, what we're talking about here, is a step-by-step process. It's sort of lengthy. It's not difficult, but it is a step-by-step process. So first step, you have a balanced chemical equation. Second step, identify the oxidation numbers. Third step, identify what's being oxidized. Fourth step, identify what's being reduced. And you get how many electrons are lost in the oxidation by looking at the change from -1 for the iodide ion to a +5 for the iodine in the iodate ion. And then the reduction of chlorine 0 oxidation state to a -1 oxidation state. All right, I don't really have much to say here other than the only thing we didn't really do that I didn't stress is make sure you balance the atoms. So make sure you balance the atoms on the half reaction. So if we go back, this chlorine, there was 2 chlorines here, so don't forget the 2 there, that you've got to balance the atoms. Up here on the oxidation, you have 1 iodine on both sides. That's balanced. Don't worry about the oxygen or hydrogen. So let's see, did it say that on this slide? So I would say that if you want me to add an extra bullet to this is don't worry about, do not worry about, about oxygen or hydrogen. That's what we'll use that to balance the redox reaction. All right, so assign the oxidation states by determining the element oxidized, the element reduced. Again, you should have already done that with your your initial oxidation states. Oxidation electrons should be on the right. Make sure they're on the right. That means you're losing those electrons. Reduction, the electron should be ahead of the arrow. All right, so here's the next part. Balance the half reactions. So this is, I would focus on number 3 the most. This is where I think a lot of students miss it. So 3 is probably the most important. So you balance all other elements other than hydrogen and oxygen. You add water where you need oxygen. You add hydrogen ions where you need hydrogen. And if the reaction's done in a base, you have to neutralize the hydrogens that are hydrogen ions left over with hydroxide ion. And I'll show you how that works. Make sure the reactions are balanced, both charge and both elements. Add those together and make sure in the end that all the atoms are accounted for and the total charge on both sides of the yield sign are exactly the same. All right, so you're going to get plenty of practice with this. You have to go algorithmically through these steps, and if you do that and you're methodical about it, then you should be in good shape. And to me, this is on par with, you know how we did the indirect method, Hess's law for delta H, and then Gibbs free energy in the last chapter. This is on par with that. It's the same type of process. It's step by step by step. You just got to follow the steps. 1 through 7, bam, bam, bam. Don't change it. Don't skip. And the other thing you need to know is the oxidation numbers. All right, so let's look at this problem. This is a real simple one. This is about as simple as I get right here. So the first thing you want to notice is what kind of solution are you talking about? Well, it's an acidic solution. That's important. So that means if there's hydrogen ions left over, that's fine because it's an acidic solution. So make sure you read the reaction carefully because it could be acidic or basic. If it's basic, you have to get rid of the hydrogen ions. This one says acidic. So this one you're going, well, there's no hydrogen oxygen in it. You're right. So this is making this a really easy problem. But what you need to do is you still need to go, okay, this has a 0 oxidation state. The oxidation state of this is positive 2. The oxidation state of this is positive 3. And this has a 0 oxidation state. So you got to break it down into its 2 half reactions. So you're going to have aluminum, and I'm not going to worry about the states of matter for this, all right? Aluminum goes to aluminum 3 positive. So tell me, is that oxidation or reduction? It's oxidation. So you lost 3 electrons. The elements are balanced. The charge is balanced. That is the oxidation half reaction. All right? So the other reaction has to be a reduction half reaction. Well, we have copper 2 positive, gains 2 electrons, and it becomes copper solid. Or just plain copper. So I'm not worried about the states. You should, but like I said, I'm just skipping that. All right. So that's the reduction half reaction. And you know it's a reduction half reaction. The electrons are on the reactant side. You know this is oxidation. The electrons are on the product side. This aluminum lost 3 electrons. This copper 2 positive gained 2 electrons. So my half reactions are balanced as far as charge and number of elements or atoms. Now, in order for you to add these 2 half reactions together to get the reaction that you see up here, these both have to have the same number of electrons being lost and gained. So this one is losing 3, aluminum's losing 3, copper 2 positive is gaining 2. So you have to think about what number do 3 and 2 both go into, and that's easy. That's 6. So you got to multiply this entire equation by 2. You got to multiply this entire equation by 3. And by doing that, you will get 2 aluminum reacts with 3 copper, 2 positive ions, yields 2 aluminum, 3 positives, plus 3 copper solids. Same number of copper on both sides, same number of aluminum on both sides. Total charge on the reactant side, this is 0. This is 2 positive. 3 times 2 positive is a positive 6 total. And then 2 times the 3 positive here for the aluminum is positive 6 because this is 0. So there's my equation. It's balanced. So that's what I'm saying. At the end, the element's got to be balanced and the charge has to be balanced on both sides. They don't have to be 0 on both sides, but they do have to have the same charge on both sides. So if it's -2 on the reactant side total, then it has to be -2 on the product side. And if it's not, you've made a mistake. All right, let me erase that so you can see that a little better. So they do the same thing. First of all, they assign the oxidation rules, numbers for each element. They identify what's being oxidized and what's being reduced. All right, they go through the procedures. There is no hydrogen or oxygen, so they balance the aluminum. They balance the copper. They know that 3 and 2 both go into 6, so they have to multiply the aluminum by 2, the entire equation. They have to multiply the entire equation of copper by 3, and then they add those two together. The electrons must cancel out. That is the key right here. This is why we multiplied by 2 and 3. The 6 electrons on the product side of the oxidation reaction cancel out with the 6 electrons on the reduction half reaction. Those have to cancel out, and if they don't, you've made a mistake. So that's what this slide is saying, is make sure at the end you've got the same number of each element on both sides and you have the same charge on both sides. If you don't, you've made a mistake. These are not hard. They are fairly easy. It's not like some hard, deep mathematical, exponential, logarithmic calculation, but it does have to be methodical, and you do have to know the oxidation number rules. All right, so let's look at this one. So the first thing that you should notice is that, this is a basic solution. That means in the end, you should not have any hydrogen ions. If you do, you've made a mistake. Okay? So the first thing I want you to do is identify the oxidation numbers of each element in this reaction. So you may want to hit pause here, see if you can figure this out, and then start up. All right, looking at this, iodine is a -1 charged ion, so it has an oxidation state of -1. Iodine on the other side is elemental iodine. It has an oxidation number of 0. The tricky one is this one. We have to break it down. I don't know what the oxidation number is for manganese, but I do know that the rule is for oxygen, it's -2 unless it's a peroxide or superoxide, and that's not what this is. Remember, peroxides, they look like this. They're O2 with a -1 charge, and a superoxide is O2 with a -1/2 charge, if you want to think of it that way. Or it's that's probably the best way to think of it, something like that. All right, that has to be equal to if you look at this has to be equal to the charge on the manganate, which is -1 per manganate. Yeah, let's get it right. So you ought to practice on the naming too. This is per manganate, all right? So if we solve for this, we get x minus 8 equals -1, so x is equal to a +7. So we now know this is a +7, and the oxygen is a -2. Well, what is it over here? Well, it's x plus 2 times a negative 2 equals 0. Again, why does it equal 0? Because there's no charge on this substance. So here we're going to get x minus 4 equals 0, x equals positive 4. So we went from positive 7 to positive 4. So this is going to be our reduction half reaction. So let's do that. And we can see then that that has to be oxidation. And it is, because we're going from a negative 1 to a 0. All right. So now you know what your half reactions are. So you know that you have iodine negative 1. And we're going to make that 2 of those. And that's going to become iodine plus the loss of 2 electrons. So there is my balanced half reaction. The elements are balanced. The charge is balanced. And so the only thing you may do differently, you may just say oxidation. Make sure you make that note that this is the oxidation half reaction. So the permanganate, you got MnO4 negative, and that's going to MnO2. And so let's look and see what needs to be balanced here. So we have 1 manganese here and 1 manganese here. We have 4 oxygen here. We have 2 oxygen here. So I need 2 more oxygen. So the rule says if you need more oxygen, add water. So we're going to add two waters to the product side. All right, so by adding 2 waters, now I have 2 times 1 oxygen. I've got 4 oxygen on both sides. But because I added water to the product side, I now have to add 4 hydrogen ions to this side. All right? So that I've got a total of 4 hydrogen on the product side. I've got 4 hydrogen ions on the reactant side. And then, so we've got the manganese are balanced, the oxygen is balanced, the hydrogens are balanced. What's not balanced? What's the charge? So in order to balance the charge, you have a total of, right now, 3 positive on the reactant side. 4 positive plus the negative 1 is 3 positive. And you have 0 charge on the product side. So I need to add 3 electrons to the reactant side. So by adding 3 electrons to the reactant side, the total charge on the reactant side is now 0, and the total charge on the product side is now 0. So charge is balanced, number of atoms are balanced. This reaction is done. And we know that this is a reduction half reaction. Again, why? Because the electrons are on the reactant side. Whereas if the electrons are on the product side, it's oxidation half reaction. All right, so we got the same problem here we had in the previous problem. This is the oxidation half reaction is losing 2 electrons. And the reduction half reaction is gaining 3 electrons. So what do 3 and 2 both go into? So we'll multiply this oxidation half reaction by 2. We'll multiply the reduction half reaction by 2. Yeah, 3 for this one, 2 for that one. I don't know if I said 2. 3 for this one, 2 for this one. All right. So when we multiply those out, well, we're going to see it. So I'm going to write that down. Maybe hit pause. So write this down. I'm going to erase it. And so we've gotten through the worst part of it. So let's follow through it. All right. So we did that. We did that. All right. So here is where we're balancing everything. So here they, yeah, I don't really like, I mean, they're showing it. They're showing that the iodine is fixed. They didn't show the electrons for it. Yeah, I don't really care for, let me go back. Let's see. Crap. Yeah, they're actually doing it a little differently than me. And so let me show you how I do it, and then I will go back. So what we have is we had two iodide ions forming I2 plus the loss of 2 electrons. And then below we had 3 electrons plus 4 hydrogen ions plus the permanganate yields manganese 4 oxide plus 2 waters. All right. And I said, well, you're going to have to multiply this entire equation by 3 and this entire equation by 2 and then add the 2 together. All right, so let's do that. So what we have is 6 iodide ions yields 3 iodines plus 6 electrons. And down below we have 6 electrons plus 12 hydrogen ions plus 2 permanganate ions yields 2 manganese 4 oxides. Remember, the 4 is the Roman numeral because this is oxygen is a negative 4 total, so that manganese is a transition metal, so we call it manganese 4 oxide plus 4 waters. All right. So we're ready to add these two equations together. So let's do that. The electrons have to cancel out, so that cancels out with that. We get 12 hydrogen ions plus 6 iodide ions plus 2 permanganates yields 2 manganese 4 oxides plus 3 iodine ions, or not ions, just 3 iodines, and 4 waters. Oops. Oh, yeah. Okay. All right. 4 waters. All right. Now, this is where students make a mistake. So if you leave it like it is, you're telling me this is an acidic solution, and it's not. It's a basic solution. So we got to get rid of the hydrogen ions for this to be a basic solution. So what do? Well, we add 12 hydroxide ions to the reactant side, which means we have to add 12 hydroxide ions to the product side. So whatever you do to the reactant side, you have to do to the product side. Well, these 12 hydroxide ions and hydrogen ions, they bond together and they form 12 waters. But you have 4 waters on the product side. So those 4 waters go away, and we subtract 4 from the reactant side, and we have a total of 8 waters left. All right, 8 waters. So you got 8 waters left on the product side. All right, so let me go up here and write what we have. Let's clean it up here. We got 8 waters. All right, we have 6 iodide. We have 2 permanganates. That yields 2 manganese 4 oxides, 3 iodines, and 12 hydroxide. Oops. 12 hydroxide. 12. All right. So then students say, well, I'm done. I'm finished. The hydrogen ion's gone away, and everything's balanced. And actually, let's see. I don't think something's right here. Let's see. I added 12 hydroxides to both sides. Let's see. It's 8 hydrogen ions. Oops. Yeah, I made a mistake here. I made a mistake. This is 8 hydrogen ions, not 12, right? Let's see. I multiply that by 2. It's 8 hydrogen ions, not 12. So I need 8 hydroxides. Let's change this to 8. I see a mistake here. 8 hydroxides here. So I'm going to form 8 waters minus 4. So 8 hydroxide. I still have 4 waters on this side. So that's going to change this to 4 waters. Not 8. And that's going to be 8 hydroxide here. Yeah. So you make mistakes, it happens, and let me just say, just make sure that's why you got to double check your work. So let's double check it. We got 4 times 2, 8 hydrogen here, 8 times 1, 8 hydrogen here. We've got 6 iodides here, and we got 3 times 2, the 6 iodines here, and we got 2 manganese and 2 manganese, and the total oxygen is 2 times 4 is 8, and 8 plus 4 is 12. So we got to have 12 oxygen. 2 times 2 is 4, and then 8 times that is 4. All right. One last thing to look at is let's look at the charge. We have 6 negative and 2 negative on the reactant side. That's a total of 8 negative, and over here we got 8 negative. So you might say you're done at this point, but there's one other trick they put in this problem, and that is everything everything could be divided by 2, but you would end up with a fraction here of 3/2. So I don't know which way they want you to do that. You can leave it as whole numbers, or you could divide everything by 2. They probably leave it as whole numbers. All right, so let's erase mine so you can see what's going on here. So there you have it. 6 iodide, 4 waters, 2 manganese. They leave it as a 3, so they left it as whole numbers. So you end up with the same process, and I think mine's a little easier. To me, this looks a little confusing because they're kind of breaking it out into individual steps a little differently. But either way, it still comes out to be the same answer. I like to solve it as a acidic problem and then correct at the end for the acidity. They corrected right up here at the very beginning with acidity. I wouldn't have done that, but that's up to you how you want to do it. I believe I also have another redox balancing, if you just want to focus strictly on that, on my Professor Chemistry channel as well. All right, so you'll come up with the same answer. We come up with the same answer, but they are doing it a little differently. All right, this is where this video will stop. The next video we'll talk about electrochemistry and electrochemical cells, whether they're voltaic, which is spontaneous reactions, or electrolytic, where they're non-spontaneous redox reactions. So again, this is where delta G comes into play, and so we'll look at cell potential and the relationship to delta G in the next video. Thanks.